Taylor's theorem. The conclusion of the mean value theorem can be presented as such. This relation suggests that it might be possible to extend this result to include higher order derivatives under suitable conditions. The corresponding formula would appear to be as such, where C is bound between B and A again. Now this is Taylor's theorem. Now more formally, suppose f possesses derivatives of all orders up to and including n-1th order. Now derivative on the closed interval AB if f and its first n-1 derivatives are continuous on the closed interval A and B. 2, f as an nth order derivative on the open interval A and B, then there is some number C such that C is contained within B and A, and our theorem, our equation is given here. Now a proof of this. First we construct a suitable function g and then apply Rolle's theorem. In this case Rolle's theorem has been used repeatedly. We define the function g by this here, where the number k is chosen so that g of b equals g of a. The value of k is therefore this given here, which all of this divided by b minus a to the nth power, and this is our k value. Now the function g is continuous on our closed interval AB and differentiable on our open interval AB, and g of a equals g of b by Rolle's theorem. There is some number c1 with which is bound between b and a such that our g prime of c1 equals 0. Now differentiating this from the box above, we have this equation here, and therefore g prime of a equals 0, assuming that n is greater or equal to 2. We see that the function g prime is continuous on a c1 and it's differentiable on a c1, and g prime of a equals g prime of c1 equals 0. By Rolle's theorem, there is a number c2 such that a is less than c2 is less than c1 is less than b, and g double prime of c2 equals 0. And we can check by differentiating that g to the k of a equals 0, where 1 is less than or equal to k, which is less than or equal to n-1. In particular, if n is greater or equal to 3, then g prime of a equals 0 equals g double prime of c2. And applying Rolle's theorem to g double prime on a c2, we obtain a number c3 such that a is less than c3 less than c2 less than c1 less than b, and g treble prime of c3 equals 0, and we can continue in this way and repeat the process further n-3 times to obtain a number c of n such that this from the box above. Now g to the n of x equals f to the n of x minus k to the n factorial on x bounded between b and a, and therefore this equation gives, writing c in place of c of n, gives f to the n of c n factorial of k. When combined with the equation for k, we obtain the required result. And that was Taylor's theorem.